Okay, section 10.1 is called an ideal transformer with an imperfect core. In the chapter 9 ideal transformer model, we had this core that was what we called infinitely permeable. And there were no limitations to the amount of flux that we could derive from this. And you could think of it as in terms of I could continue to increase current, and I'm going to get flux, and there's no cost, so to speak, for this. But what we're going to find out is that's not the case, and we can easily model the actual core, and by adding two elements in parallel with the core. And so let's look at what that looks like. Okay, so what we know is that the iron core, perfect core, has to be replaced because the practical transformer has a core that has hysteresis and eddy current losses, and the permeability is lower than we looked at with an ideal transformer. And we can represent these imperfections by adding a resistor and an inductor in parallel with the primary terminals of this ideal transformer. And so that's what we're looking at here. So we're going to add this resistance and this inductor, and we're going to put that in parallel with the primary terminals here. And so that will account for this hysteresis effect and this eddy current effect, and also this idea that this whole thing is not infinitely permeable. So when we look at this, we see that the primary is excited by this source E sub G, and it produces an induced voltage E sub 1, right? And this is that induced voltage that we looked at, and how that occurs within the transformer. And even though it's in parallel here, right, we understand that it's an induced voltage, and this is the source voltage that causes the induced voltage. So the resistance R sub M represents the iron losses and the heat that they produce. Okay, and those iron losses, we can think of that, in terms of these eddy currents that are forming within the core, and the heat that's generated because of the circulating currents. And so what we're showing here, in addition to that, is that the current going through this parallel resistor, we're going to label it I sub F. And I'm guessing that the I sub F is, representing the atomic symbol for iron, Fe. And so that current is shown here. Okay. Now the second part of this, the inductor, it's probably not quite as obvious in terms of what's going on here, but the magnetizing reactance, this X sub M, is a measure of how permeable the transformer core is. So if the permeability is really low, then X sub M is low. And I want you to think about that in terms of this current. Okay? So this current that's flowing through this inductor represents the magnitude of the current that we need to create the flux in the core. All right? Now, if this takes a lot of current, a high value of current, then that means that X sub M is very low. Okay? Why is that? Okay, so we have a voltage, right? We have a voltage, and say it's divided by X sub M, the inductive reactance. Okay, so think about this. So if this is very small, this number X sub M, then that's going to make the current large. All right, and that would say that it takes a lot of current to go through here to get a certain amount of flux out. But at the same time, were this a higher value, right? If this were a higher value, then we're getting the same flux out regardless. We learned that earlier. Then this current would be lower, and that would actually indicate a higher permeability. Okay, I hope that makes sense. He says that the magnetizing current needed to create the flux lags 90 degrees behind E sub I. Okay, so the current, in an inductor, the I sub M is going to lag this voltage, E sub 1 by 90 degrees. All right, so that's that classic Eli relationship, where the current lags the voltage by 90 degrees. All right, so that's that part of it. We can actually determine the values of the R sub M and X sub M. And we could do this by connecting the transformer to an AC source unloaded, and we can measure the active power and the reactive power, with a watt meter and a var meter. And so, based on these equations, and for the first equation we'll solve for R, and the second equation we'll solve for X, what we could do is we could derive these equations 10-1 for the value of R sub M and the value for X sub M. And R sub M is the resistance representing the iron losses. X sub M is the magnetizing reactance of the primary winding, the inductive effect. And E1, these are all based on the voltage associated, the induced voltage. Excuse me. P sub M is the total iron losses in watts, because that's what we're trying to account for here, right? Are these iron losses resulting from eddy currents and hysteresis. And Q sub M is the reactive power that's needed to set up the mutual flux between the two. Okay, so the total current needed to produce the mutual flux in an imperfect core is equal to the phasor sum of I sub 1, and this. Okay, that's the current that we need to produce the mutual flux. It's called the exciting current here, and then we see it again there. Okay, and so what we can look at in terms of, and it's very small percentage of this total current. And again, remember, this is unloaded right now, and so there's no actual current flowing to the load out here. So this is kind of what we're looking at, and let's kind of look at this phasor diagram and see if we can make sense of it. Okay, so this is the total current, and as you can see, it's shared between that current that's going through that inductor and that current that's going through the resistor, that we labeled I sub F. And we can also see a couple of things here. We see all the voltages are in phase. We see that the magnetizing current is 90 degrees out of phase. And here's the magnetizing flux, which is going to model the current. And we can see ultimately that this entire current that we're accounting for here, this I sub O, is the sum of these two currents that are flowing through here. Okay, and of course that's represented graphically with this slide. Okay, so the phasor diagram at no load for this less than ideal transformer is shown here in this 10B, and we can even get a peak value for the mutual flux, and that goes back to equation 9.2. So let's look at that. And for a little, flashback to that equation 9.2, this was, that equation that we derived for, for the voltage, that we were looking at when we were doing this ideal transformer. And if we solve that for the flux, then we end up with this equation that you see on page 198. Okay, so that's where that comes from. Now, what voltage are we concerned with? Well, we're wanting to use the induced voltage on the primary side as that voltage that we look at with this. Okay, so this is the peak value. This gives the peak value of the mutual flux here. And, you know, we talked about why we use peak value in section 9. And now we'll look at section 10.1, and I'll just go ahead and include it with this video, you know, because it's not too much to it. And I think once we put some real numbers with this, you'll maybe start to see a little usefulness of this. Try to understand these relationships here, okay? You know, all these relationships between, you know, the voltages and the currents across there, you know, how they relate to each other, you know, where they would appear on this model, and so forth. Okay, so let's pause this and we'll do this example right quick. Okay, so I added some of the values to this figure before we actually work this example 10.1. But it says a large transformer operating at no load has an exciting current that's equal to 5 amps. Okay, so that's this. And we know that that is comprised of this current and that current. And he says when the primary is connected to a 120 volt source at 60 hertz. Okay, and he says from a wattmeter test, it's shown that the iron losses are equal to 180 watts. And again, these iron losses, you know, the eddy currents and hysteresis, they can be reviewed in that section 226 through 229. And he asked us, first off, what is the reactive power absorbed by the core? Okay, well, reactive power is, you know, we can get there. We can get there using these topics back from 135, where we looked at apparent, reactive, and true power, or active power, whichever one you want to call it. And, you know, we know that relationship. So he says, what is the reactive power of the core? Okay, so the apparent power, S, is going to be E sub 1 times this current, okay? And that's going to be 120 volts times 5 amps, or 600 volt amps, okay? Now, that doesn't really get us anywhere, does it? That's just one component of this. We know that the iron losses, the active part of this, they're given to us as 180 watts. Okay, now, hopefully you remember this. S squared is equal to P squared plus Q squared, right? And we have this, and we have that. So what we'd like to get is Q squared. So, I mean Q, so Q squared would be apparent minus active, square root of this, square both sides. Q is equal to 600 squared minus 180 squared, square root, and that is going to give us 572 volt amp reactive, and that gives us the answer to part A. Okay, so that is the total reactive power absorbed by the core in this inductive portion of that. Okay, let's chew on that for a second. So in part B, he's asking us what the impedance corresponding to the iron losses and what is the magnetizing reactance. Well, we have this for the iron losses. So I put in my 120 squared. Didn't like that. Let's try this. There we go. 120 squared. and that's divided by 180. Okay. And this is going to come out to be 120 squared divided by 180, which is going to be 80 ohms for the iron losses. And the magnetizing reactance, the X of M, is 120 squared again, divided by 5, excuse me, let's square that, not degrees, right? And divided by 572 var. And he says that X of M is 25.2 ohms, and that will take care of both of those. And then finally, in part C, he's saying what is the current needed to supply the iron losses that we have calculated. And we can easily find this I sub F, this guy right here. And what do I need to get rid of? I need to get rid of something so we can see this, don't I? Let me erase all this. So I sub F, okay, this portion of this, I sub F is going to be the voltage, 120. All this is in parallel, divided by 80. And that is going to be 1.5 amps flowing here. Okay. Similarly, on the other side, again, it's 120 volts because all this is a parallel. And this is 25.2 that we calculated here. And that current is 4.8 amps. Now, when we get into this world now that you guys are dealing with, you know, this is nothing simple anymore, right? So this is a phasor addition that we have to do, all right? And so what we're trying to calculate is this current that, you know, is being supplied here. It's not a simple addition of 1.5 and 4.8. We have to look at this in terms of gosh, I'm trying to talk here, the phasor sum of these two. So let's see if I can find that for you. I think I've got a diagram that shows, and we can put these values there. Okay, so here's what we've been working on, right? This is the I sub O, you know, and we determined, you know, the two components of this, the 1.5 amps that is supplying the iron losses and the 4.8 amps that are supplying the magnetizing current. And so if we put that in a phasor diagram, we can see that here, right? Since this is resistive, you know, we see it in phase with the voltage. And this is through an inductor. So it's going to be 90 degrees opposed to that. And then, you know, we can do the summing of this, the total current, this I sub O, this 5 amps, we know what the answer is. And so it is going to be I squared F plus I squared M, and that would be 1.5 squared plus 4.8 squared. And if you do all this, plug it in and roll, you'll end up with 5 amps, which we thought that would be from there. And these are the phasor relationships of that. Okay, so, you know, not the easiest thing in the world, but nothing here that you shouldn't be able to comprehend and work with. You know, just sort of bringing all this stuff together. And I think, you know, the further you go with this world that you're in, the more of this you're going to see. But at the same time, I think for those of us that are really into this, it really starts to become interesting. And these relationships allow us to go into areas that, you know, the complexity increases, but I think at the same time, the interest and the fascination part of this increases too. So Rather long video, and I apologize for that. Maybe I should have split this up into two, but that's section 10.1. It goes faster through the rest of this, I promise you.